Hello, my name is Richard Golden, and this is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. I'm from the University of Texas at Dallas, and the title of my talk is Estimating Parameter Confidence Intervals in Possibly Misspecified Parameter Redundant Models. So a fundamental modeling challenge is that we are often faced with the question of whether we're going to work with a flexible model or a constrained model. Flexible models have many parameters. Constrained models have few parameters. Flexible models, you might be able to fit all the data points. Constrained models, you won't be able to fit all the data points, but you might be able to pick up some of the important statistical regularities. Flexible models are widely used in machine learning. The focus is on prediction, not explanation. They've been used to solve some really complicated tasks in artificial intelligence. And constrained models are often preferred in mathematical psychology. The goal is explanation and prediction. And we also want to model very complex phenomena as well. So flexible models tend to be correctly specified. They tend to fit the data. And constrained models with fewer parameters tend to have more difficulty fitting the data, but that means that they're falsifiable. Flexible models also have lots of parameters so that they're more prone to overfitting, while constrained models are less prone to overfitting. They have less parameter redundancy. A flexible model tends to be characterized by non-identifiability, which means that you might have two different parameter vectors that are quite different, but nevertheless provide equally good fits to the data. So this can lead to ambiguous interpretation as to what the parameter values mean, and it can also lead to possible problems in consistently estimating those parameter values. Constrained models have less of a problem with the identifiability. But what do we mean by the concepts identifiability and parameter redundancy? So let's look at those concepts a little more carefully. So there's this counting rule, which is often used as a heuristic rule in modeling, and it basically says that we want to make sure that we have more data points than parameters. And this was discussed by Bamber and Van Santin in a 1985 article published in the Journal of Mathematical Psychology titled, "How Many Parameters Can a Model Have and Still Be Testable?" And they point out that the matter of determining whether a model is testable is substantially more complicated than the counting rule. And this is because the correspondence between the parameter values and predicted outcomes need not be one-to-one. You may have a complicated nonlinear relationship. So let's take a closer look at a more sophisticated notion of parameter redundancy. So a model is called parameter redundant if we can express that model as a model with fewer parameters without changing the set of probability distributions which is represented. So in this example, we have a probability model with 3 probability distributions represented by 4 parameters. And if we can represent these 3 probability distributions by just 3 parameters, then we would say that the 4-parameter model is parameter redundant. Now, there's a theoretical result which says that if we construct if we're doing maximum likelihood estimation, and we take the log likelihood per observation and take the derivative of that, then the expected value of that derivative of the log likelihood per observation times its transpose defines a matrix. And if that matrix is positive definite at a particular, say, critical point of the expected negative log likelihood function, then the model is not parameter redundant near that point. And the proof is straightforward, but I don't have time to go through it, but it's here if you want to look at it later. And so there are many close relationships between identifiability and parameter redundancy, but these are really distinct concepts. So let's now look at identifiability. So the concept of local identifiability means that if we have a particular parameter vector theta star, we say that theta star is locally identifiable if no theta near theta star specifies the same probability distribution. So in this example, theta star would be considered locally identifiable since we don't have a parameter vector near theta star that specifies the same probability distribution. Now, in this example, we have theta 3, which is pretty close to theta star. And so we would say theta star is not locally identifiable. And there's a theoretical result which says that if we take the second derivative of the negative log likelihood function and evaluate it at a critical point, then if the resulting matrix is positive definite, then that implies that that critical point is locally identifiable. And again, this is a pretty straightforward proof. I'm just sketching it here. You can look at it later if you wish. So in summary, we've talked about the idea that the positive definiteness of this matrix B of theta star, which is based upon the first derivatives of the log likelihood function, indicates parameter redundancy near theta star. While the positive definiteness of A theta star, which is based upon the second derivatives of the expected negative log likelihood function, says something is a sufficient condition for local identifiability near theta star. Now there's an important equality which has been around for a long time, and it basically is called the information matrix equality. It says if the data was actually generated from the probability distribution when we plug theta star into it, then A of theta star has to equal B of theta star. And in addition, a classic asymptotic statistical theory of maximum likelihood estimators assumes that both the A theta star matrix is positive definite and the B theta star matrix is positive definite. If these two conditions are held and theta star is a critical point, then the asymptotic distribution of the maximum likelihood estimates is Gaussian with a particular covariance matrix, which is actually expressed in terms of A theta star and B theta star. So this leads us to the new stuff. The information matrix equality holds only when the probability model is correctly specified. Yet there's few discussions in the literature of how the failure of the information matrix equality affects criteria for identifiability and parameter redundancy specified by A theta star and B theta star. So, and in fact, the assumption of that the IM equality holds is often made without any justification or discussion of model specification. So the question that I'm interested in investigating in this talk is, what are the consequences of model misspecification for estimation and inference in the presence of parameter redundancy and non-identifiability? So I'm going to start with this method I call the linear projection method, and it's pretty simple. But basically, the idea is we're going to constrain the parameter space by projecting theta into a lower dimensional subspace through a linear projection. So we're basically equivalently specifying the null space of this projection is basically specifying the subspace we want to omit from our model. And let me show you a little bit how it works. So here we have a two-parameter model, and this is a contour map, so you can see that there's a strict local minimum here. So this would be a locally identifiable model. And then here, for a three-parameter model, there's a third parameter, but here we can vary the third parameter quite a bit, and it doesn't change the value of the strict local of the local minimum. So so in this case, we don't have any sensitivity of adjusting theta of one of the parameters to when we change it. It doesn't affect the value of the negative expected log likelihood function. And so we have a situation with where we don't have local identifiability. So what we're going to do is we're going to take the three-parameter model and project into a lower dimensional subspace using this projection operator, P star transpose. And also this can be applied to saddle points. Saddle points come up quite frequently in complicated probability models. For example, in latent variable models, they're almost inevitable. And in practice, we might be interested in looking at a critical point associated with a saddle point, because it might be that the Hessian at that point has many positive eigenvalues and just very few negative eigenvalues. So we would qualitatively, this would be a saddle point that's almost, but not quite, a strict local minimizer. And so we can use this method if we wish to construct a projection matrix so that the projection of the critical point theta star into a reduced subspace is in fact a strict local minimizer. Basically, we are going to say we're not interested in the subspace where associated with these negative eigenvalues. So here's some theoretical results. Basically, the idea, though, is we're going to take we have theta stars as a critical point of the expected negative log likelihood. We compute the second derivative of the expected negative log likelihood and find the eigenvectors with the k positive eigenvalues and make those columns of the matrix P star. And then we're going to use that projection matrix to project theta into a psi space. If we do it in this way, it turns out, this type of construction, that this will ensure that in this new parameterization, you see how I've written theta dot double dot as a function of psi. In this new parameterization, that the function L psi of psi, which is basically could be equivalently thought of as the expected negative log likelihood function defined with respect to a constrained parameter space, is locally identifiable. And then it's straightforward to establish consistency of the constrained estimator using standard classical arguments. And it turns out that you can also characterize the asymptotic distribution of the maximum likelihood estimates. And this is a theoretical result. It's straightforward. But the basic idea is simply that we can show that weighted sums of the original maximum likelihood estimates will have an asymptotic Gaussian distribution, even if the distribution of the joint distribution of the original maximum likelihood estimates is not asymptotically Gaussian. And even if the covariance matrix of the original maximum likelihood estimates is singular. For example, this occurs if you have more parameters than observations. So, and here's a specific, and you can actually get a specific formula for the covariance matrix, which is expressed in terms of the projection matrix and the A and the A of theta star and the B of theta star matrices. And it reduces a special case to a simplified formula in the case of when the model is correctly specified. And again, to emphasize that you can have situations where the number of free parameters is less than the number of data points, and the theory still remains applicable, provided we check certain conditions. And here's a sketch of the proof, which I don't have time to go into, but it's pretty straightforward. And we have experimented with this and did a simulation study where we, with my, this work done with my PhD student, Candice Participo. And basically, we took the Tasuka's 2015 question fraction subtraction data set, fit it to a cognitive diagnostic model with 30 parameters, sampled with replacement from the fitted cognitive diagnostic model to create 100 data sets, each with 20 simulated participants, each answering 15 questions. So we basically have fitting a model with 30 parameters to a sample size of 20, and then we re-estimate the parameters. And we managed to get some fairly good confidence intervals. Some of these confidence intervals are tighter, and some of them are wider for the different items. But but we have sort of a nice empirical illustration of how this might work. So in summary, non-identifiability, parameter redundancy, model misspecification are inevitable during model development for as well as for well-established models with quality data sets. We introduced the linear projection method for constraining the parameter space to ensure local identifiability. Even when the covariance matrix is singular, subsets of parameter estimates or linear combinations may have well-behaved asymptotic Gaussian distributions. And these preliminary simulation results illustrate some key ideas showing confidence intervals for a locally identifiable but parameter redundant model. And here are some references.